So the next thing we'll go over is how to program 3-axis toolpaths. Were there any questions on the 2-axis toolpaths in here so far?
No.
Okay. Okay, so the part what I have here is basically a cavity, and it was imported into SOLIDWORKS. So you can see that you can work with IGES files, step files, parasolids, so pretty much any solid geometry that you can bring in. I wouldn't recommend working with STL files because they aren't handled very well for representing the model. So they try to convert each of the facet that you see into a face, so it becomes very hard to program STL files. But for any solid surface geometry that's IGES step, any of the solid surface models, you should be able to efficiently program it. So workflow is very similar. You bring in the part, you establish the machine tool, define the number of axes in here, and then you select your post processor. You can choose to output in inches or millimeters, and then you define your workpiece. In this particular step, I'm going to define as a box stock. And now I'm ready to program some toolpaths. So before I program the toolpaths, I'm going to put my work zero to the top and then the southwest corner right here. And then I would start with a roughing process, a 3-axis roughing. I can pick a tool for it, 1/2 inch end mill, set the feeds and speeds, and specify your clearance definition, your cutting parameters. You can fill in the parameters for cut levels, like how much of material you would like to take out per pass. And then finally, you hit generate. So your toolpath is now programmed, your roughing toolpath. You can go to the Simulate tab and run a verification. And you could always do a pause and then pick Simulate to end to run through the simulation. Now, once we're through with the roughing process, we could go back and program a pre-finishing or a finishing toolpath. So I'm going to start with a pre-finishing pass. I'm going to use parallel finishing. I could now select a boundary to restrict the toolpath if I don't want to mill these flat faces in here. I can click on Select Curve Edge Regions and just pick this boundary around it here. I can say Select Tangency, so it picks the chain of the face edges around the part. We'll grab a tool. We'll go with a 1/4 inch ball mill. Specify the cutting conditions in here. We can set the step over. I'll put in 20% of my tool diameter and generate it. So in this particular step, you have a pre-finishing toolpath or a finishing toolpath. So this is called parallel finishing, which basically follows in parallel planes following the 3D model. So the angle of cut is set to 0, which basically runs parallel to your x-axis, following the model back and forth. Now with the Pro configuration, you have more options for programming 3-axis toolpaths. You're not just limited to parallel and horizontal finishing. You could actually program much more methods like 3D step constant, 3D offset pocketing. You could do projection pocketing. You could do pencil tracing or remachining. So there's a lot more options that are offered to you in the Pro configuration. Would there be any questions so far? So I'm going to hit the pause button here, and then I'll pick Simulate to end, and you'll notice that it basically runs through the simulation and shows you the result. Now with the parallel finishing, the way the nature of the toolpath, you're going to end up seeing some of these scalloping in here because it's riding parallel to the vertical surface. So you may have to program at a secondary toolpath with in a different cutting direction in here to clean these up. So that's how you typically have to do it, if you're using just a parallel finishing operation. Now, some of the benefits of using the advanced 3D methods in here, let's say we want to do the 3D offset pocketing, which is offered to us in the Pro configuration. So I'm going to pick the same loop around the part, and in this particular step, I could choose to start the boundary from the outside, work its way in, and this is going to basically result in a constant 3D step over, or also known as uniform 3D step over. So some systems call it constant scallop machining or uniform 3D step over. So it maintains a constant uniform 3D step over as it follows the boundary that you picked and onto the 3D model. So as you can tell, this method has a little bit more computation involved, so it could take anywhere from a few seconds to a couple of minutes to generate the toolpath. Now while this toolpath is being generated, would there be any specific questions I can answer?
No.
Okay, so as you can tell here, the toolpath is just generated, and you'll see that it creates a uniform 3D step over. So there's a nice transition in here in these areas as well. So this method is called 3D offset pocketing. Now there are several additional methods like 3-axis pencil tracing and remachining. So I'm going to use an example to demonstrate that. Now before I do that, once you have these toolpaths programmed in here, you could post-process them out to your machines. Right-click and then select Post. Then you specify the file name. So by default, it'll use the name of the part and also add the name of the setup to it. And I hit Post. Now if the part that you're working with requires programming from additional sides, so let's say you had some holes in here or some pockets in here that you need to machine, in those instances you would have to actually go ahead and create additional setups in here, and we'll talk about that in just a moment. So this is basically the G-code output for just programming from the orientation, like looking top-down into the cavity in here. It automatically outputs your tool numbers and also calls for the tool changes as we go through the programming in here. Any questions?
No.
Okay. Now to program, be able to program from additional sites in here, you would have to create what is called a new setup. So if you're manually flipping the part and refixturing it in the machine, you add a new setup in here, and you change the orientation for machining. So you could rotate it by 90 degrees on the x-axis. So let's say you had a pocket or you needed to drill some hole in here. So you basically orient the coordinate system so that the z-axis is normal to this particular face, and then you can add in machining operations in here. You can see that there's a new setup added in here, and you can create 2- and 3-axis operations. So for example, if I want to add a pocket, I can choose pocketing. I'm going to pick this boundary right around the part. I can use select loop, put the loop on the part. I can grab a tool in here, so I'll go with a 1/2 inch end mill. I'll specify to leave some stock around the part, and I'll give it a depth of 100 thousandths cutting in and generate. So you can see that the tool is actually cutting into this, so I just put in a pocket, leaving 100 thousandths from the edge of the part. So now when I run a verification in here, so I have the parallel finishing simulated. I haven't simulated the 3D offset pocketing, so I would need to simulate this operation before I can simulate the pocket operation in order for the in-process stock to remain on it. So you can see this 3D offset pocketing is following along the contour of the part as it steps down. And you can always do a pause and then hit simulate it to end, which will simulate it to the very end and show you the result of the simulation, so you don't have to have it run through the simulation. I can see with the 3D offset pocketing, it results in much nicer finish on the part. Now let's go ahead and run the simulation for the pockets. You can actually simulate it from multiple orientations as well with the Pro configuration. So you can see that the pocket that we added is being machined. So the part actually you would have to rotate it on the machine and orient it this way, so you would be able to build this pocket in here. Would you have any parts that require machining from more than one side?
Yes.
Okay. So this is one of the benefits of being able to do it in the Pro, so you can program from multiple different orientations within the same part without having to create multiple copies of the part to program from each orientation.
So would there also be a visualization of each setup side by side if you did, had machining on a number of sides, or is it one setup at a time displayed?
Yeah, each setup. So now if you take a look at the setup number 2, it actually shows what you had on the previous setups as well. So it shows it's a continuation of what you already programmed, right?
Okay, yeah. So then you would, but if let's say you had, we envision having 3 clamps side by side, maybe, and rotating the part from the top to the left to another face with a different G code for each position. So can you visualize that too with Visual CAM, or is it?
Yeah, so what we do here is just output the work offset number. So for example, for the top machining of the top features in the part, you could be using a G54. For machining of the side face, you could be using a fixture offset number G55. So you can basically output them. So we're not going to visualize them side by side. We're just going to show them how you have it programmed in here. So this would be a G55 coordinate position, which is basically you can specify where it needs to be in here. So I can specify to maybe put it to the right over to this corner in here. And then that would basically represent where your origin is.
Okay. Yep.
There's only one stock blank that's going to be displayed in here during simulation, but you may have it put it on a different wise, as you're programming it. So this is what outputs your G54 or 55 or 56, the work zero. And you can output each setup to a separate setup information sheet, which is the shop documentation we were looking at from the previous example. Okay?
Mm-hmm.
Would that help?
Yes.
Okay, great. Now, we talked about feature detection and machining in for prismatic parts. Now here, if you have a part that has a 3D cavity in here, you could still do a feature detection on it. So you can basically identify the features on this part by just selecting the top face, the planar face right in here, and this will go ahead and identify these features. So it identified the face and also a pocket feature right in here. So it shows the pocket feature. Now you can select right-click on this pocket feature, and you can program a 3-axis roughing operation, very similar to how we programmed it by just by not using the feature detection method. So you can hit generate, and it will create your 3-axis roughing toolpath. So for cavities, if you have cavities in a part, and you can pick the top face, which is typically planar, to also be able to program using feature detection. Would there be any additional questions about this particular example we looked at?
Let's say on setup 1, use a 1/2-inch end mill, and setup 2, use a 1/2-inch end mill. When you go to run your program in the machine, is it going to do a tool change back to that 1/2-inch end mill when it goes to setup 2?
Yes, so here we have a 1/2-inch end mill on setup 1. So basically, you go from an end mill, then you're going to a ball mill in here, a 1/4-inch. So as you change tools while programming your machining operations, it's going to just follow the same sequence. So if you wanted to do the, if you wanted to maintain the same tool, then you basically, have another setup in here and go back to setup 1 to do the parallel finishing on a separate operation, or you could just post these 3 operations in here to one output file. And then you can post this setup to one output file to eliminate a tool change.
Okay. So setup 1 and 2, that's still the same program, right? Like if you go to
You can
post
have them
it?
as 2 separate programs, or you can have them all in one program. So if you right-click on the machining job and select Post All, it's going to post Setup 1 and Setup 2. Now, since you're working with a 3-axis machine tool, you'd have to pause to either change, or if it's just another fixture you have it on, then you don't even have to do a pause, right? If you're going to manually rotate this part or refixture it, then you would have to basically stop the program and refixture it into it. But if you already have, a WISE1 and WISE2 that are oriented the part correctly, you just right-click on the machining job and do a Post All.
Okay.
Am I making sense?
Yeah.
Okay, great. Would there be any other questions?
Nope.
Okay. Now I would want to go over a couple of other 3-axis methods. These are called advanced 3-axis methods, where we can look at pencil tracing and remachining. So I have an example here with some toolpaths already programmed on it. So we've already looked at the horizontal roughing toolpath in the previous example, parallel finishing. We can also program radial machining in here, so where we can actually pick a boundary, and it'll basically, the toolpath will follow along the boundary. You can also program the offset pocketing, similar to what we looked at in the example. We have additional methods like, the toolpath morphing between two curves. It's called between two curve machining. So you can pick two open curves or two closed curves, and the toolpath can actually morph between the curves following the 3D models. It's called between two curve machining. You can program pencil tracing and remachining for, cleaning up areas on these scallop areas on the model, where it automatically identifies bitangencies on the part and determines the areas that needs to be cleaned up. So there's a lot of different types of methods that are offered to you in the Pro configuration, where you can choose different methods in here. You can also do roughing and re-roughing. So for example, if you did a roughing operation with a large cutter, so I'm going to switch this cutter from a 1/2 inch to, let's say I want to put in a 3/4 inch end mill in here. So I'll add a new tool. So I'm going to define this as a 3/4 inch end mill. And in the cutting parameters, I'm going to specify these parameters. I can say bottom of cut, not to cut below a certain Z. I can restrict it. So if you have any clamping or anything, you can specify your bottom cut containment, set the engage and retract, and then pick generate. So in this particular process, it's taking into account your part and the stock and establishing your roughing toolpath. So if you're using a larger cutter to rough it out, so I'm going to hit play to run the verification. And you can always do a pause, simulate, and to run through it, all the steps. Now you'll notice that the cutter is unable to get into some of these areas in here because the cutter was way too large. So rather than having to use a small cutter and go back and rough the entire part, with the Pro configuration, you can go from a roughing to a re-roughing operation. So the re-roughing operation will take into account the in-process stock. So I can go from a 3/4 inch flat to a 1/2 inch, or I can even go smaller. I can add in a tool in here. I can go with a 1/4 inch. I'll save this up as a new tool. Use the same cutting conditions in here and generate. So in this process, the re-roughing operation takes into account what's being left from the previous step and creates a roughing toolpath just on those areas. So you can see that it's trying to get into all of these tighter areas to clear them out. So it's not roughing based on the entire stock material that's that you're starting out with, which is the box stock, but it only looks at the areas that are being not cut from the previous operation. So there's the result of the initial roughing, and then after the re-roughing process. So it takes it as close as possible to the finished shape of the part. So you can do multiple iterations of re-roughing with smaller tools. You can also limit them by specifying boundaries only to re-rough in certain areas as well. So this is also one of the very nice features that you get as part of the Pro configuration.
Well, one maybe you touched on here in this last one was, just let's say you're holding this part down with some clamps that rise up, on the side of the part. For one, doing the avoidance and then also just the visualization, can you bring in and visualize where maybe certain type of clamps are, and then also to avoid those areas? How do you go about that?
So one of the things you could do here is, you can use a Z containment like we talked about, or you could even pick boundaries from the part. So for example, I could say I would like to not go past this boundary in here, so I can pick a loop around the part, and I can pick this as my entire boundary loop. So the cutter will completely stay to the boundary. That's not going to go past it on the sides. So you can see that the toolpath is now being contained just around this area. Now, if you wanted to actually model something in here, you can actually create like a block that represents your your clamp or whatever you're holding, or you can even insert them into this, and you can use them. You can create basically areas not to cut into by defining boundaries in here. So this is one of the ways I would do it. I'm sorry, go ahead, sir.
Oh, yeah, no, so you would end up drawing that or pulling in some assembly that, I mean, there's quite a bit available online, but you would pull that into the assembly then. And,
so you have to save it out as a part from an assembly and then So for example, I can go ahead and say, this is where my clamp is going to be. So I can just put in a block that's slightly larger than the X, Y, and the Z extents, right? So I can throw in a rectangle in here, and now I could go over to, I can extrude this over here to represent that this would be my clamp. I'm going to do an extrude boss. I'm going to pick that sketch right here and say this is where my clamp is going to be, right?
Okay.
So now when I add this in, it actually treats this also as part of the part geometry. So if I program a toolpath in here without defining any containment boundaries, the cutter is not going to cut into it. It'll skim above that. You see that, sir?
Mm-hmm.
So you could actually define these areas that you don't want to cut into, and you can also pick boundaries around it. Now, for example, if I want to do a horizontal finishing toolpath in here, I'm going to go ahead and, I could have added a boundary over on the side. This is for the purpose of illustration in here. I'm going to go ahead and put a sketch in here by picking this plane, and I will just throw in a rectangular boundary in here. Okay? And I'll go ahead and delete this one out. I don't need this boundary right here. I just need one of these. So now I'm going to go ahead and add a 3-axis horizontal finishing cut. So do a finishing in levels using horizontal finishing with the boundary selected. I'll just pick a tool, go with a 1/2 inch ball, and then generate it. So you'll notice that even though I have a clamp over on the side, it also treats it as a geometry, so it's not going to cut into it. So it's basically the cutter will ride over it, as you can see right there. So if you place a box that's slightly larger than, what the extents of your clamps are, you'll notice that it's not cutting into it, right? So you can use different ways, different techniques to basically specify your avoidance areas.
So yeah, one question would be again, and maybe I didn't make it quite so clear myself. Is there a library of clamps that one can import in and put in the assembly, or do you in general go to this route of adding an extrusion to indicate where a clamp would be?
Yeah, we do not have any specific library of clamps in the CAM programming part of it, so there's something that you can probably have to look at if SOLIDWORKS has like a toolbox where you can find those, or you may have to build something in there and you can use it on other parts. So, we treat everything what you see here as basically the part. So it's not going to cut it, whatever that's inside this, because the cutter will not gouge into those areas. You know what I mean?
Yeah.
You can pick areas that you want to avoid in some operations, like in 2-axis, where you have an operation, like say, for example, we have a facing operation. We can pick avoid regions to avoid, like for clamps. Those can be done by just creating some sketch geometries around it in here. So if I go ahead and grab the sketch in here, I'm going to do a select chain. I'm going to go normal to this view here. I can add a secondary sketch. I'll say I want to model a new sketch, and I can throw in areas where I wanted to have some clamps in here. So I can put in a sketch right in here, and also I'll throw in a sketch right in here. So I have the sketch drawn in here. Now I could program a 2-axis facing, and I'm going to say select curves. I'm going to select this chain right in here, and then for avoid areas, I'm going to select these 2 boundaries in here. So I have these selected, and I can specify a tool for it. And when I generate the toolpath, it'll automatically treat those as areas not to be cut into. So that's the way we handle avoid areas. So you could be drawing just as simple as a rectangle that represents the extents if you're programming like a 2D operation. In 3-axis, you basically have to extrude them, so it's slightly larger in X, Y, and also in the Z, so to avoid any collisions with your clamp.
Okay, so spots where the clamps are, let's say we're still in first setup, but we want to clean up those areas after. Like, but
Okay,
still,
so you just want to go back and clean up these areas in here, so you could program a toolpath just for these areas in here as well, so you can define a boundary to program those areas. So if I had a clamp in here, for example, the solid model, I would like to go back and profile cut these areas. I can suppress this feature and go back and machine those areas out. So in SOLIDWORKS, you can go to your history tree. You can just do a suppress area right there. And now I can go back in here to my horizontal finishing. I can add a new operation in here to just select this area out.